Just do a quick audio check. Hopefully you can hear me all right. Just yeah, so we'll get started in a few minutes. So no stress. Hello, welcome. Please let me know if there's any questions in particular you'd like me to work on. I will try my best to get through as many questions as we can, but obviously if there's any area you'd like to work on in particular, then please let me know in the chat. There's benefits of coming here. I'm always happy to look at particular sections. Welcome. We'll probably start at 12:05. Let me here is the paper that we're looking at. It is the final exam that I did for my course. All right. Is there any questions in particular anyone wants to work on? Surely there's some area because I know I have my own strengths and weaknesses. But I really like Laplace. So if no one's going to give me other questions to work on, I'll just do most of the Laplace ones. I find it nice, convenient, but they're a bit tricky to start with. Do get it wrong. A bit hard to first wrap your head around. But once you've wrapped your head around it, yeah, question 4, of course. We can work backwards, actually. Question 4. Yeah. Okay. Well, we might as well get started. That's it. All right. So, actually, I'll squeeze this in. So, we're asked to find the inverse Laplace of h of s is equal to s squared minus 5 on s of s plus 1 squared. Okay. What are people thinking is the best way to find the inverse?
You'd probably just partial fraction.
Partial fractions, very good. So we're going to have some form of a on s plus our now b on s plus 1 plus cs on s plus 1 squared. Is that correct? Or is there more to this b and c? I'm thinking it should just be c. Does that look familiar?
Yeah, I think, yeah.
S of s plus 1 squared. Okay, and then we'll get it with our a of s plus 1 plus b s plus 1 plus cs. And we want to make sure that that is equal to s squared minus 5. So then we'll have s squared is equal to as squared plus bs squared. And then we're going to have 0s is equal to the s squared plus 2s plus 1. So then 2as plus bs plus cs. And then minus 5 is equal to a. That's nice and convenient. So that tells us that a is equal to minus 5. Then b is equal to 6 from the top one. And there. And then c will equal minus 10 plus 6 plus 4. Okay. And then, so we're going to have our minus 5 on s, if I could. Minus 5 on s plus 6 on s plus 1 plus 4 on s plus 1 squared. And then this is going to be, we can look at the start, where we have, so we have 1 on s is u of t, 1 on s plus a, e to the minus at, and 1 on s plus a squared is t, e to the minus at. Okay. So then minus 5 u of t plus 6 e to the minus t plus 4t e to the minus t. Let's show u of t, u of t. Okay, and that is the final answer. Any questions with that? Nope. Okay, I'll assume it's all good then. Alrighty, and now we have, let's get to the poles and zeros. Now, when do we have the poles and zeros? Who remembers?
Zero is when like the numerator is 0, and pole is when the denominator is 0.
Very good. Now, what symbol do we use for poles and which symbol do we use for zeros? For zeros, we use circles. For poles, we use crosses. Okay, so this pole here will be when we have root 5. Right, so we have a double 0 at the 5 here. So we will go here twice. All right, and the same double of 5 or root 5. Okay, and then we have for the poles, we have s for the 0, so we have 1 here, and we have it at -1 twice. Okay, so we have a double here as well. And then we have 1 here. Okay, does that make sense?
Yep.
Now, is the system stable?
Yes, I think.
Very tricky question, isn't it? Because we have these zeros here, so we're not sure. Did the zeros cause instability? So you've got to remember, we only referred to the poles when we looked at stability. Since we have this guy here on the 0, it's marginally stable. If it was on the left, it would be stable. If it was on the right, it'd be unstable. Does that make sense?
Yeah.
Okay. Alrighty. So that was AI and II. So then, for the circuit shown in Figure 8, show the working, find the values of the capacitor C to yield a critically damped response. 4 marks. Use Laplace transform to find an expression for VC of t, for ti, tau, greater than equal to 0, using the value of C from part I, where U of t is a unit step function. Okay. Now, what do we need for the system to be critically damped? Let me just try and draw this over here. Plus or minus VC of C, 2H, L, 8, U of T, and 12. So what do we need for a critically damped system?
Was it alpha equals to omega for the characteristic function? Or?
Very good. Very good. Now we have the s squared plus 2 alpha omega plus omega n squared. Is that what it was?
2 alpha s or?
Yes, there is an S in here. Very good spot. Now when we're trying to find the general equation for it. And so when we'll need to find some differential equations to sort of solve for this system. Now, it doesn't say, right, what we need to do actually for it. Right, just need to find a value for the capacitor C to yield critically damped response. Okay. Now I'm gonna sort of do the Laplace transform just to make my life easier for myself. That way I know. Now, first off, we have U of t. So what are our initial conditions going to be?
B equals 0.
B equals 0. Very good. Makes our life very easy. Okay, so 8 U of t just becomes, I'm going to go blue here, 8 on S. 12 is just 12. C becomes 1 on SC. And then 2H becomes 2S. And so then we have a voltage, H on S, is equal to the current flowing across all of these. So it's going to equal to 12 plus 1 on SC plus 2S multiplied by minus IL S. Okay, so for IL of S is just going to equal this 8 on S times it by 12 plus 2S plus 1 on SC, CS, whichever way you want to do it. Okay, and then you're going to end up with 8 times CS, all on S of 12 CS plus 2S squared C plus 1. And now we have 8 CS and S. They cancel out nicely. And so you end up with 8C all on 2S squared C plus 12 CS plus 1. I don't know why I put brackets in there. Shouldn't have brackets. Okay. And so then we can divide by 2C everywhere. And so we're going to end up with a 4 on S squared plus 6S plus 1 on 2C. Now this is where you can start looking at your alpha and omega to sort of get those values. All right, but I just know that we go S squared plus 6S plus 1 on 2C. And I need that to equal S plus A squared to be critically damped. Plus 2AS plus A squared. So therefore 2A is equal to 6. And A is equal to 1 on 2C. Therefore A is equal to 3. So then 9 is equal to 1 on 2C. So C is equal to 1 on 18. Does that make sense? Or do you want me to go over that again? Please let me know if I'm going too fast or I'm going too slow. It's really hard to judge when I can't see any of your. I'm going to give a quick summary of what I just did. And probably the best place to start with is this here. Okay, we are looking for critically damped. Now, critically damped occurs when the poles are in the same location. So that's why we're looking for an S plus A squared on the bottom. Okay. So that means if I can find my transfer function, like this one up here, I will have it where I have some poles at the bottom, which should be in the form of S plus A all squared. So what I did was I went around trying to find some sort of transfer function for the amount of current flowing through. So I could then get my final equation answer where C is equal to 1 on 18 because I solved it of S plus A all squared. Now, you could have also used the knowledge that we know that it's when alpha is equal to omega from this understanding. Okay, but I prefer solving it that way. That's just me. Any questions with that? Nope. Okay then. All right. Now, use Laplace transforms to find an expression for VC of t for t greater than or equal to 0 using the value of c from part I, where u of t is the unit step function. Well, lucky for us, we just found it in terms of IL. So then we just need to find VC is equal to IL multiplied by 1 on SC, because it's just the impedance of the capacitor. So therefore VC, the trick is though, they want it in terms of time. So we'll need to bring it back. VC of S is equal to that answer that we had there. And we know that C is 1 on 18. So then we have 1 on 2 times 1 on 18, which is just going to give us 1 on 9, which just gets you 9. Okay. So we will have 4 on S plus 3 squared times by 1 on S times C, which is 1 on 18 times 1 on 18. Yeah. Which is going to equal, zoom in, 4 times 18, all on S of S plus 3 squared. And we could probably see where this is going. So A on S plus B on S plus S plus 3 plus C on S plus 3 squared. And then we're going to have A of S plus 3 squared plus B of S plus 3 plus C of S. Now we know that we have A of S squared plus not 2. Should be 6AS plus 9A plus BS squared plus 3BS plus CS. And that is all going to equal 4 times 18, 2 times, which is 72. So we know that 9A is equal to 72. So A is equal to 8. And we know that A is equal to minus B. So therefore B is equal to minus 8. And then we have 6A plus 3B plus C is equal to 0. And therefore we get C equal to 6 times 8 minus 3 times 8 is 24. So it's equal to minus. Minus 24 on S plus 3 squared. Okay. And then we will get 8 minus 8 e to the minus 3t minus 24t e to the minus 3t u of t. And there we go. Does that make sense?
Yep.
All right. Anything else you'd like me to work on with that particular question? Or does that make sense? Would you like me to finish with C or move on to a different question?
Yeah, I think C is good.
C is good. So skip C.
Oh, like let's do C probably.
Let's do C.
Yeah.
Okay. That's all right. We're just like not quite sure what that means. All right. So the current in a 40 ohm resistance is this. where u of t is step function, showing we're working, find the Fourier transform of the current I omega of t. Now, it's probably been quite a while since people have looked at the Fourier transform of a signal. Now, luckily, it is at the start in the formula section. Essentially, we're looking at x of w is equal to the negative to positive of 20 e to the minus 2t u of t e to the minus j omega t dt. Okay, so what should we do from here? Is there anything that's jumping out at you?
You can remove the uniform and then make the bounds 0 to infinity.
Very good. So then it's just going to go between 0 to infinity. We can put the 20 at the front. We don't really care about that. E to the minus 2t, e to the minus j omega t dt, which is going to give us 20 e to the minus t of 2 plus j omega. All right, which I'm just now going to skip a step and go minus 2 plus j omega, bounded between 0 and infinity, which is equal to 20 on minus 2 plus j omega. E to infinity is 0, 0 minus 1, which is just going to give you 20 on 2 plus j omega. Now, we know from, if we have e to the minus 2t u of t, we scroll all the way up to the top. We can see we have our Fourier transform pairs that, where is a good example? That e to the minus at is equal to 1 on s plus a. And we know that the Fourier transform is a special application of the Laplace. So it's just going to be 1 on j omega plus a. And then we just have that factor of 20, which was out the front. Which shows 20 on 2 plus j omega. Okay, please check your working. All right, that quick little check, make sure, or tells you whether or not you got the correct answer or not. Does that make sense?
Yeah, so good.
Okay, that's good. Yeah, we're just trying any way that we can to try and make life easier for ourselves. So this is just going to be I of omega is equal to that. Now, sketch the amplitude spectrum, absolute value of I of omega as a function of omega, clearly marking at least 3 amplitude values at different frequencies. Okay, so what do we expect this to look like? Well, we could break it into the real imaginary parts and whatnot, which not a bad idea. We can multiply this by 2 minus j omega on 2 minus j omega, so that we can get with 20 on 2 minus j omega all on 2 plus omega squared. So I don't have the imaginary part on the bottom anymore. And then I want the absolute value of it. So it is equal to the 40 squared plus the 20 omega squared all over 2, 40 on 2 plus omega squared on 2 plus omega squared, and then we want to square that, and we want to square that, and we want to take the square root of that to get a magnitude. Now, it's probably just going to be 40 squared plus 20 squared omega squared, all on 2 plus omega squared squared. And let's get rid of that. So we'll just take that and then that on there. So it's just going to be a 40 squared plus 20 squared omega squared. Square root of that. All on 2 plus omega squared. Okay, does that make sense what I did so far?
Yeah.
Okay. It's been a long time since I've done it as well. Don't worry. Now, if we plug in omega equal to 0, then that'll go to 0, that'll go to 0, and you'll just end up with 40 on 2, which is 20. Now, if omega is equal to, omega squared is equal to 2, and we can have 40 squared plus 40 squared. So then you're going to end up with 2 times 40 squared, and take the square root of that, all on 4, which you can just plug it into a calculator just to get an answer rather than having to worry about that myself. Could probably pick a nicer number, to be honest, just like about 14.14. So it's definitely going down. And then as omega approaches infinity, we are eventually going to get a omega squared square root on omega squared, which is going to be omega on omega squared. So it's eventually going to go to 0. Maybe something like that. And then I put that point there as omega equal to root 2. You get you 14.14. And this point here, omega equal to 0. And I'll leave you guys to pick a final point. Say omega approaches infinity, goes to 0. Okay, does that make sense?
Yep, so good.
All right. And then find the percentage of the total energy dissipated in the resistor that is associated with the frequencies in the range of 0 to omega, listen to root 3. Okay. Now, do we remember how we deal with power in the frequency domain? It's someone's formula that we've used.
Is it like Parsifals or?
Parsifals. Very good. Now, I don't remember Parsifals off the top of my head, so we'll have to hopefully look at the top and see, is it at the top here? Oh, there you go. It gives you it here. The critically damped one. It does not give us Parsifal's theorem. Alas, we will have to make do without it. Okay, so find the percentage of the total energy. Now, what is energy? Yeah, I know it seems like a weird question, but you know, energy is just going to be the voltage. Power is the voltage times the current, and energy is just power times time. All right. So, since we have this power times current, then we can also say, well, it's the same as current squared times resistance. Right? So, if we can get some understanding of the current, we can square it and then get the power of the resistor. Now, if we look at this shape, if we go between 2 root 3, that's going to be somewhere here, right? Now, the energy stored over time will actually be the area underneath this curve. So what we want to do is we want to go back to this expression that we have here. So we can use this one here, and we want to integrate that. Oh, I didn't want that one. Oh well. So we want to take the integral of 40 squared plus 20 squared omega squared over 2 plus omega squared. I'm going to the square root of that. Now what we can do is take a factor of 20 squared, which will give us 40 squared is just 20 squared. 40 squared divided by 20 squared. It's just times 4, right? Yes, it's 4 plus omega squared. Okay, which is nice because then we can take that out and we're just going to have the integral of 20 the square root of 4 plus omega squared all on 2 plus omega squared. And we're integrating that between 0 and the value they gave us, which is 2 root 3. 2 root 3. It's not very nice to integrate, is it? Looking at this, it's sort of like a partial fraction sort of thing. Now, I actually haven't asked, is it an open book or a closed book exam?
I think it's open.
Okay, well, lucky for you guys, yeah. Because if you get a question like this and it's an open book, you can just chuck that into some sort of calculator and it'll calculate it for you, like MATLAB or Wolfram Alpha. You can also look up Parseval's theorem rather than trying to come up with some version of yourself.
I guess that's the way they expect you to do it. I'm assuming, probably, right?
Well, I mean, it's not looking the most convenient. So I'm thinking yes, but it was open book for us when we did it. So, where is it over here? Yeah, Parseval's theorem is the 1 on 2 pi of the integral of minus infinity to infinity of the absolute value of g of omega squared dw. Ah, isn't that nice? So that squared deals with our nasty square root that we have here, which will then become our 1 on 2 pi of the integral minus infinity to infinity of 20 squared 4 plus omega squared all on 2 plus omega squared squared, which sure isn't the nicest, but it's better. But yeah, I'm guessing just plug it into a calculator to solve. Okay, any other questions with question 4? No. Alrighty. Do we go to question 3? We'll go question 1. Question 3. Okay. Which one in question 3 do you want to do? Or do you want to do all of them? Well, I think the first one's a bit tricky. And should seem familiar. It's similar to what we had to do in Tute Lab 2 when we had to analyze that circuit. Now, normally we would just put it in the parallel resonance circuit where it's the 1 on LC, omega naught is equal to 1 on LC, right? The square root of 1 on LC. Okay, however, we have a resistor and an inductor in series with each other. As such, we can't do that. Does that make sense? So, how do we have to analyze this? What do we need for resonance condition?
Like the impedance of the capacitor and inductor should cancel. So you have a purely real.
Mm-hmm. The real is an element of any number, any real number, I guess. But yeah, it's mainly solving that imaginary part equal to 0. Very good. Okay, so looking at this circuit, do we want to find the reactance or the admittance? So do we want to find Z or Y?
Probably Y.
Y. Very good. And the reason for that is because we've got, they're all sort of like parallel components. Now, I actually was doing this one to make sure I was prepared. So we can see that Y is just going to be the first component, which is the capacitor, plus the 1 on R plus J omega L. Okay. And then what we're doing is we're just combining that across. So we get J omega C of R plus J omega L plus 1. Now, please see how here there are C's and L's. Don't sub them in just yet. It's a lot easier to write this than it is to sub them in. Okay, and so get to this point and you just expand it out. And now you want to remember, we have this imaginary part on the bottom. So we must multiply this by R minus J omega on R minus J omega L. Does that make sense?
Yep.
Okay, so you just go through and then I just collected anything that had a J because I don't care about the real part. Okay, so you get this, and then you have these two conditions when omega equals to 0 and when omega squared L squared C, this which gets you omega is equal to L minus C R squared on L squared C. And then I checked this number with LC Spice. So I know it's correct. Does that make sense? You probably wanted to leave it in terms of omega because it said to find that they wanted to find omega naught, but I just wanted to check with LT Spice to make sure I wasn't crazy. Does that make sense?
Yep.
Alrighty. Okay, so then looking at the next question, the circuit shown in figure 6, if the initial charge on the capacitor at t equals 0 when switch is closed is 20 volts. So 20 volts. Then showing the working state, the type of response I of t for t greater than or equal to 0. What sort of response are we going to get? That is looking at these type of responses. Overdamped, quickly damped, underdamped. Now, not doing it any part of the question. If we had to guess, which one would we guess it to be? Any guesses? You got a 1 in 3. I'd say it's pretty good. Overdamped. Not bad. Not bad. Why do you think overdamped?
It was a guess.
Just a guess? That's fine. That's fine. I sit here and I see I have an inductor. All right, I have a capacitor. What normally happens if you have an inductor and a capacitor? Energy will flow this way, energy will then flow that way.
Yeah. Oh, okay.
All right. So that to me makes it seem like it would be, all right, a bit of bouncing.
Yeah.
What type of response is that?
Underdamped.
Underdamped. There you go. All right. So it's small little things that looking at going, oh, let's see, can it help us figure out what it is? All right. And then this is by deriving a differential equation and following natural response solution methods, find an expression for I of t. So honestly, you could state the type of response based on that, but you can sort of do II and use II to prove I. So, all right. Voltage across an inductor is equal to L di dt. And then voltage current through a capacitor is equal to C dV dt. So we are looking for I of t. So therefore, voltage across the capacitor is equal to I of t times R plus, well, it's going to be some, what am I doing? I times R plus voltage drop across the this capacitor. Okay, and I'm now going to add an extra page in. Okay, so we have voltage across the capacitor is equal to I of t R plus voltage across the inductor. And now we know that voltage across equal to I of t R plus, now V of L is equal to L di of dt. And now we know that I of capacitor is equal to C dV dt. So we need to take the integral of that, or we take the derivative of both sides. So then we get dVc on dt is equal to di tr dt plus L di squared on dt squared. And so then I can replace that with IC on C. Correct, yes, cool. Is equal to R dic of t plus L dic squared on dt squared. And so then that'll give us our dic squared on dt squared plus dic on dt times our R on L plus our last one, which would be plus minus IC on LC. And that is equal to 0. Okay, and then S squared plus R on LS minus 1 on LCS. If I was to solve that, looking at the top, we can see that that would be the point. We can just sort of solve it to figure out where the roots are. That's what I always do to make life easier for myself. I'm going to have our S plus, what am I doing? S is equal to negative R on L plus or minus the square root of 4AC So 4 on LC minus, that shouldn't have an S. What am I doing? Please stop me if I've made a mistake anywhere. L squared on L squared plus 4 on LC on 2A is equal to minus R on 2AL, where A is 1. All right, plus or minus this R squared, L squared. Is that correct? Could someone please check for me? Could be. Easiest way to check, Laplace transform. All right, so we would have VC of t is equal to R I plus ISL. And now we could replace this with the current flowing up through there, which would be our I times our 1 on SC. Because essentially the current flowing through this way, the velocity drop across this will equal the velocity drop across that. Okay. And so we should get 1 is equal to RISC plus no longer having I's, I's should just be SC plus S squared LC. And then that tells me that still think I made a mistake somewhere. Anyway, we'll keep going. It's that idea. Does that make sense?
Yep.
Yep. That's right. And then, yeah, so we just keep going and following natural response solution for final expression of I of t. So yeah, so once you get that, you just sort of solve for a natural response. So we know eventually it's going to go to 0. That's convenient because eventually all the charge will dissipate. Alrighty. Now, C, final expression for the network transfer function VMS about the voltage gain, assuming 0 initial conditions. All right, so we're looking for V2 on V1. V2 on V1. Come on, pen. On V1. All right, that's good. All right, and it's just a voltage divider, right? Q plus ZC, or R plus ZC on R plus ZC plus R2, which is just going to equal to Q plus 1 on J omega times 0.03, all on 6 plus 1 on j omega times 0.03. Okay. And then because we would have had r plus 1 on j omega c on r plus r2 plus 1 on j omega c, we're going to times this up. So it's going to go to there, it's going to go to there. So we're going to have 2 j omega times c plus 1 all on 6 j omega c plus 1. You just do the times 1 minus j omega c6 on 1 minus j omega c6, which is then just give you the 1 plus 2 j omega c and 1 minus j omega c6 all on 1 plus 6 squared plus omega squared plus times I don't c squared. Okay, does that make sense?
Yep.
Just a lot of calculations. That's really all it is. And then we ask, guess the poles and zeros of h of s. Well, oops. They want it as times of s. So replace all those with s, which makes this a little tricky. So what you want to do is just go back to here. We don't need to do this. This should be, this becomes s, and this becomes s. So you get rsc plus 1 on r plus r2 sc plus 1. Which in this case is relatively nice to solve. You get 1 plus s times 2 times c all on 6 s c plus 1. So then the zeros would just be s equal to minus 2c, 1 on 2c. Then the poles would be s equal to minus 1 on c6. Does that make sense?
Yep.
Please let me know if I'm going too slow, going too fast. Always happy to change. If you just want me to keep going, I can do that too. And then sketch the poles and zeros for part 1 on the S-plane, identifying all key points. We're going to have 1 at that location, and then 1 maybe at that location. I don't know exactly where they are, but you get the idea. And for part I, otherwise sketch the magnitude response, h of j omega, as a function of omega, clearly marking at least 3 magnitude values at different frequencies. So we sort of did that before, just times it by the real thing. And then you essentially just expand this, so you'll end up with 1 plus 2cs on 1 plus 36s squared c, because we times this by 1 minus s6c, 1 minus, which I already put in there. I'm jumping a couple of steps, but you get the idea. So then you get 1 minus s squared times 12c squared plus 2cs and 1, and then 1 minus, and then minus the s squared of that one plus the 2cs minus s6c, all on this 1 plus 36s squared. Then you can do the substitution that s is equal to j omega, because then the s squared, not going to have to worry about it. And then you can just plot the real part squared square root of the real part plus the imaginary part squared, like we did before. Does that make sense?
Yep, it's all good.
Yeah, cool. Then for part I, otherwise sketch the phase response as a function of omega, clearly mark at least 3 phase values at different frequencies. And so once we have this expression, we can just get the phase response by doing the tan inverse of the imaginary part on the real part. I think that's what it is. Don't quote me on that. But
yeah, I think so.
Yeah, hopefully that's right. Okay. Then we get to question 2. I'm going to work my way backwards this time. Why not? Change it up. So the first one here, we have a 2-port network, which hopefully you remember from this week's shoot lab. Okay. Now, there are 2 ways we can sort of solve this. We could set V2 to ground, and then we could try and find Y11, and then Y22 and whatnot. However, please be mindful of there'll be a lot of calculations involved for that. Or, because it's a nice simple network, I'm going to denote this point here as VA. Okay, and so essentially what I'm going to do is I'm going to do V1 minus VA on 2 is equal to I1. Right, and we know that V2 minus VA on 4 is equal to I2. Okay, and then we know that I1 plus I2 is equal to VA on 6. And we know that V1 is equal to I1 2 plus VA. Therefore, VA is equal to V1 minus I1 times 2. Because essentially we are looking for I1 is equal to V1 minus VA 2 on 2. And we know that VA is equal to V1 minus I1 times 2. Problem is, if we sub that in, that's just going to cancel out. So we don't really want to do that. Okay. But we know that VA, we want to try to get in terms of V2 and V1. Okay. So we know that V1 minus VA on 2 is equal to VA on 6 minus VA minus V2 on 6 plus VA minus V2 on 6. All right, it's just the voltage drop across here. Well, the current flowing through this way is equal to that plus that. Hopefully that's all clear. We have V1 on 2 is equal to now, we're just trying to collect these VAs. So we'll have VA of 1/2 plus 1 on 6 plus, that should have been a 4. Plus 1 on 4. Minus V2 on 4. So then we get VA is equal to a 6 plus 1/2 plus 4 gives you 11 on 12. So V1 on 2 plus V2 on 4 is equal to VA on 11. And so therefore we can go back to I1 is equal to V1 on 2 minus, now instead of VA, we're going to replace that with 12 on 11 times 1/2 of V1 on 2 plus V2 on 4. So then I1 is equal to V1 of 1/2 minus 3 on 11 minus 6. So you choose 3 on 22. V2. Okay. And now that value there and that value there, including the negative, is y11 and y12. Okay, and now since you've already gone through the effort of finding VA, we have this expression here. Okay, so we can simply say that V2 on 4 minus V1 on 2 plus V2 on 4 times 12 on 11 times 1 on 4 is equal to I2. Okay, so then I2 is equal to your negative 6 on 11 times 4 V1 plus V2 of a quarter minus, so we get you 3 there, so 3 on 11 times 4. All right. And then that's your second one and your third one. Okay, so there's nothing wrong with shorting them out. If you find that method is easier, go for it. Nothing wrong with it, just short them out and solve. I find that if you combine them, it makes it a little bit trickier, but it saves you time, which can be quite beneficial in an actual exam. Does that make sense? Maybe?
Yeah.
Hopefully. Okay, that's good. Right. Now, going to question 3, we see in this for the circuit shown in figure 3, where you have to use a unit step function using Laplace transform methods and showing all your working, find the response I of t for t greater than or equal to 0. Well, lucky for us again, u of t, initial conditions are 0, don't have to worry about it. And this is 7 on s plus 6, this is 4s, this is 3, and this is 5. Find the response I of t. So we are going to have 7 on s plus 6. The current flowing out through there is equal to the voltage drop across this, which will be V on 5 plus V on 4s plus 3. So we get 7 on s plus 6 is equal to V and on 1 on 5 plus 1 on 4s plus 3. Okay, now we know that, so you have voltage drop across there, voltage drop across there. Now, I of s is equal to the voltage drop across this entire thing divided by 4s plus 3. All right, because we're just looking at the impedance for it, right? So when we go to expand this, I'm trying to squeeze it in so I don't have to go to the new page. We end up with 4s plus 3 plus 5, all on 20s plus 15. All right. So I'll go to the next page. So we have 4s plus 8, all on 20s plus 15 of 7 on s plus 6 is equal to v, and we know that I of s is equal to v of s on 4s plus 3. So v of s is equal to 20s plus 15 times 7, all on s plus 6, 4s plus 8. And then we're going to get an I of s is equal to 20s plus 15 times 7, all on s plus 6, 4s plus 3, 4s plus 8. Now, I know that looks horrible, but we see here, this is a factor of 5 times 4s plus 3. So then that should give us 35 on s plus 6, 4s plus 8. Take out a factor of 4, and we have 35 on 4, s plus 6, s plus 2. And we're just going to have an a on s plus 6 plus b on s plus 2. And then you solve a of s plus 2 plus b of s plus 6 is equal to the 35 on 4. And then you have a plus b is equal to 0. 2a plus 6b is equal to 35 on 4. And so therefore you're going to end up with b is equal to minus a. So then you have 2a minus 6b. So then it's going to become minus 4a is equal to 35 on 4. So a equals to minus 35. No. On 16. And then b is equal to 35 on 16. And then take the Laplace inverse, which is nice, because it should just be 35 on 16 out the front of minus e to the minus 16 plus e to the 2t minus 2t u of t. Okay, does that make sense?
Yeah.
Unfortunately, yeah, it's just a lot of calculations. That's really all it is. Okay. Now, I am going to put this before. Squeeze it in there. Okay. So, given that e to the j omega naught t is equal to this, if f of t is equal to this minus that, showing all working, derive the Fourier transform. What we should be thinking, well, we know that cos of x is equal to e to the minus x plus e to the minus x ix all on 2, and sine of x is equal to e to the plus ix minus e to the minus ix all on 2i. Okay. And so from there, we know that if we have this form, we get that. So I would expect to get 6 pi Dirac of omega minus 50 plus 6 pi Dirac omega plus 50 plus minus 2 pi Dirac omega minus 150 minus 2 pi Dirac omega plus 150. Does that make sense? Just don't forget these halves. So then that'll be divided by 2, like I just did. I clearly forgot the halves. So then that becomes 3, 3, and then it's going to have that, should be 2 pi on j, 2 pi on j. Okay, and so then when you sketch the magnitude for it, you would expect to see 3 pi, 3 pi, and then 2 pi, 2 pi. Just be careful of the phases, because they will be the same, the phases, but these ones here will be different. Pretty sure it should look like that for the phases. I'm not 100% sure. These might alternate, but that's the general idea. Does that make sense?
Yep, it's all good. So I think you just you skip the step where we change it to e's, but Like that's essentially what you did, right?
That's it. Yeah.
Yeah. Okay.
I changed it. I know that cos and sine are e's, and we know they have that relationship, so that's why I just jumped to that step.
Yep.
Okay, and then the first question was basically come up with this. Well, it's not really, but it's close enough. We have e to the minus at u of t minus e to the at u of t. Finally, from that, if I actually scroll down to, where did we do it? Here. We did it for the positive side. So it's the exact same idea. You do one for positive, one for the negative, and you get one as that, and one is the other one. And you can quickly check with the Fourier transform pairs at the top of the sheet, just to make sure that your answer is correct. Does that make sense?
Yeah.
Okay. Now, magnetically coupled circuits. I'm hoping we're okay with these. Just want to be adding in our dependent sources. Make sure that you have the pluses on either side. And then now this current enters this dot. So this will be J omega M. In which case this one, we change this because I already gave it to you as J60. So it's going to be J60 times I1. And now this one's flying out of the dot, so it's going to be minus I2 of J60. Okay, so then you're just going to have 141 is equal to I1 flowing through this 2 plus J40 minus I2 J60. And then you look at the other one. Then we're going to have our I2 times 200, also across that, is equal to the voltage gained along there. So it'll be I1 J60, the negative because it's flowing up through it, plus your I2 J60. And then you're just solving two simultaneous equations. Okay, once we found a value for that, hence or otherwise find the impedance seen by the source. Once we have this current, we have this voltage. Normally, whenever we have dependent sources, what would we do? If we want to find impedance seen by the source. We're thinking maximum power transfer. So because we have dependent, we would want a dummy source. Does that make sense? Essentially what we're going to do is going to treat that as a dummy source. 141 volts. Yeah, good enough. So then V Thevenin is just going to equal our voltage divided by our current. When the voltage is this, the current is what we just calculated. And that's your answer. Does that make sense?
Yeah.
Okay. Now for probably the hardest question, in my opinion anyway. I don't like power. So we want to sketch the power triangle for the source, and we're told it's lagging, so it's just going to be this. So we have S, Q, P. We've got some theta value. All right, now P is equal to 55K. W. All right, and then we're given our power factor is equal to 0.65. And so we can just use that in order to calculate the values for it, right? You know, Q is equal to tan of theta. P, theta is equal to cos inverse of the power factor, and then absolute value of S is equal to P squared plus Q squared, and square root of that. Happy with that? Okay, then find the value of the capacitance C that when connected in parallel with the load will produce a unity power factor. Now, we know we're going to have some Q that we're going to produce there, which is going to be this value. Oh, not that one. Yep. Some Q value there. Right. So then all we want to do is we want to say that the Q of the capacitor is equal to Q of the inductor. Let's get to oppose it. As such, we have a value for QC, and we know that QC is equal to VRMS squared all over X equivalent. Now, X equivalent is equal to our, what's this? 1 on J omega C. Did I do that right? Yes. Now, I'm not going to worry about this J because I'm only interested in QC. So that's why the K, the V, or the J is in impact. So therefore, we can say that QC is equal to VRMS squared all on 1 on omega C, which then QC is equal to VRMS squared omega C. So then C is equal to QC on VRMS squared omega. And that gets the value of capacitor. Does that make sense?
Yeah, it really feels like a while since I've done this, but yeah, no, it all looks familiar. So.
Yeah, no, I know that feeling.
Yeah.
That was me preparing, being like, how do I do this again?
Yeah.
Then we get to this next question, which is, okay, with the capacitance C from part II still connected in parallel with the load, determine the apparent power supplied by the source. Now, the apparent power is S. How much power is supplied by this source when we have unity power factor?
Just the real power?
It's just the real power, right? So then this power is equal to the absolute value of S. Right? Or more accurately, the other way around, but yeah. Is equal to P. Now, what is the apparent power consumed by the load? Is it the same value? See now, if we have the capacitor here, right? This is the load. As such, the S value here will not equal that S value.
Yeah.
It'll be the S value we calculated up here. Now, the part I'm not so 100% sure about is if we consider this to be our new load, then it would be the same.
Yeah. Yeah.
Okay. Now, the phase angle between the source voltage and the total current supplied. Now, the good news is I do know the answer to this one because, well, the current must flow through from this device and the phase angle between the source voltage. Yeah. But all it sees is power factor equal to 0 or power factor equal to 1. So it sees unity. So the phase angle would be 0 degrees.
Yeah. Yeah.
They should be in phase. And that is how you get the answers. Now, any questions on any of the stuff that I've covered?
Actually, not at the moment. I think it was actually okay. No, nothing seemed like super, I guess, unexpected or anything. So.
Yep.
Yeah.
Hopefully, yeah. Looking at the questions, they should seem similar to the Tute Labs, but
yeah, for sure.
easier than the Tute Labs.
Yeah, the two. Some of them were quite rough. Not gonna lie.
Yeah.
Yeah.
All right. So it's like this simple 2-port network, no dependent source. Long, yes, but once you understand what you're doing, it's just a lot of work. Is all it is.
Yeah.
Yeah. Some of them can be a bit tricky. Yeah. Now, what I can do is stop with that. Now, where did I chuck it to? Yeah. Any final questions for me before sort of? I'm happy to answer any other questions and whatnot.
I don't know. I always have like, as I'm doing questions, I always have something, but then right off the top of my head, not really. So
That's okay. That's okay. Yeah. I might as well share my screen for the last final bit. Okay. So something that I think is useful is we've got this course here of 2134. Where does it actually lead on to? All right. Now, the three main core courses that it leads on to is DSP, electrical energy, and control systems. Now, control systems, you're looking at more of the poles and zeros, as well as the transfer functions, low pass filters, high pass filters, and controller design.
Yep.
That's what you're looking at here. Electrical energy, you're looking more at the 2-port networks, your transformers, you're adding of capacitors in order to fix power factor, leading and lagging loads, that sort of thing. And then DSP is looking at, if you take the Fourier transform of a signal, how can we start filtering that signal? So we start looking more at the magnitude and phase responses of signals. If you're having like a radio, how can you retrieve signals from the air, that sort of thing, like radio receivers, that sort of idea.
that's not like the fun stuff, right?
Yeah, I mean, I liked control. That was my favorite. DSP is pretty cool. That's looking, yeah, it's mainly just looking at, you spend a lot of time, you've got like your signals coming through, and it's like, let's say you've got these signals, which we know as their sines and cosines. If I just want to listen to this radio station,
Yeah.
then I'll have to find a way to just extract that. And so I know it's going to be mirrored on this side. But it makes it really easy to see, oh, I'm listening to, 106.5. That's going to be this particular frequency up here, and it's going to have a couple of the music around this point. And so we have that carrier frequency set to that one.
Like, yeah, theoretically it sounds really cool, but like thinking of having to do like or like the like theory behind it kind of hurts my head a bit. So
That's okay. That's okay. Don't stress. The whole course is on that. So they don't rush into things.
Yeah.
2134 is probably the most rushed course because there's so much to cover.
What does that cover in terms of like after, like that should follow on for 2133 they should follow on for as well, right? Or
2133 covers analog electronics.
oh, okay.
So we step away from more theoretical stuff and we're going more practical. So you've got an op amp. How does an op amp actually work? Is it ideal?
Oh, okay, so, yeah.
And then you start looking at like use of BJTs and MOSFETs, so like transistor devices. And then 2141 is digital logic. So you're looking at binary tables, truth tables, K-maps. Can you follow the logical progression of a circuit? If I need to turn this on, turn this off, that sort of thing.
Oh, that sounds pretty cool, actually.
Yeah, that one's a nice fun one. That if you've done any sort of logical stuff before, you'll be like, oh, this is nice, convenient.
Yeah, I think I'm doing that next term, so.
Oh, there you go.
Yeah.
Yeah. Design 2000 is group project, and it does a little bit. Yeah. Any other course you want to ask a question about?
Honestly, I haven't looked too much into it. I've only played maybe like 2 times ahead. So.
That's okay.
Yeah, but
That's okay. Yeah. Don't be afraid to ask. Always happy to help. Okay. Well, otherwise, I think that's pretty much it I had planned for this session.
awesome. We just can we?
I'll stop the recording.